Understanding molecular machines at the nanoscale is a fascinating scientific challenge that will have medical applications and will be useful for synthetic chemistry and energy storage. For a molecular machine to work, however, you need first a molecular motor that undergoes unidirectional repeated motion that then drives the molecular machine. The problem is that such molecular motors, first, are really small, and second, their motion occurs really fast. A direct consequence of the motors being so small and so complex is that when you want to study them, let's say, for example, in a solution, you have many of them and all of them are doing something else. It's like in a football stadium where the crowd is cheering and everyone is doing stuff asynchronously. The ideal situation would be if all molecules worked synchronously, like a wave in a football stadium. So first, I will explain the motion of this molecular motor, and then second, show the experimental trick that we use to access such ultra-fast dynamics using femtosecond laser systems. And then third, these experiments are going to show whether the motion of the molecule occurs synchronously or asynchronously. And last but not least, these experiments will unveil a quite surprising truth about the molecular motors. The particular motor that we looked at is this one here. You can see it. It was first presented by Feringa, who received a Nobel Prize in chemistry for this discovery in 2016. And the motion of the motion of the motor is quite well understood. The two parts of the molecule turn with respect to each other around this central double bond, and they do this in the 4 steps that you see in this graph. How this motion exactly occurred remained unknown, and in particular the question whether step 1 after photoexcitation occurs synchronously or asynchronously. In any case, the dynamics of such processes, as mentioned before, naturally happen on very fast timescales, which means on picoseconds or even femtosecond timescales, which is 10 to the minus 15 seconds. The basic principle of measuring such really fast dynamics in molecules, for example, is the so-called pump probe spectroscopy. So we use a first laser pulse that excites the molecules and brings the system into non-equilibrium conditions. And then we use a second laser pulse, and this laser pulse then does the spectroscopy step. So we look at the properties of the molecules after a certain time delay. And by changing the time delay between the first laser pulse that launches all the dynamic and the second laser pulse, we can then take snapshots of the molecular motion as time progresses. And when we put them together, we create a real-time movie of the molecular dynamics. When physicists and chemists talk about molecular motion or configurational changes of molecules, like coming from this configuration here to this configuration in our molecular motor, which is the first step of the unidirectional motion, when physicists and chemists talk about that, they often use potential energy surfaces. Now, this may sound a bit intimidating, but simply speaking, these potential energy surfaces simply depict how comfortable the molecule feels in a certain configuration. When a switchable molecule absorbs light, it is promoted to a higher potential energy surface. In order to be more comfortable, the molecule wants to go downwards on this potential energy surface as much as it can. For the first conformational change of our molecular motor, this could either mean that the molecule synchronously traverses to the next minimum, the lowest point of the potential energy surface. In the other scenario, the molecule needs to overcome a barrier after being caught in a higher lying minimum. as overcoming this barrier would require thermal activation, or in other words, heat, the motion of the molecules in the solution would occur asynchronously, and we would only measure the kinetics of the ensemble overcoming the barrier and not the one singular time scale like in the first case. In the synchronous case, we would therefore expect a shifting peak in our spectra, while in the asynchronous case, only population would be transferred. In this case, a spectral shift could only be caused by solvation. The experimental trick to disentangle these two cases is to measure the conformational change from here to there in different solvents. If the observed time constant of the dynamics is not affected by this change of the environment of the molecules, the spectral changes are actually due to a synchronous motion of the whole ensemble of the molecules, and we are actually observing how the molecular motor moves. If the spectral changes do depend on spectral solvents, the situation is different, and we have asynchronous motion of the molecular motions that are trying to overcome a barrier. Curious? Here are the spectral changes that we observe. Particularly important is how the stimulated emission evolves. You can see here that the maximum of the distribution shifts towards larger wavelengths with time. And this is corresponding to the molecules feeling more and more comfortable. They move downwards on the potential energy surfaces. We extract this shift for two very different solvents. One is acetonitrile and the other one is N-hexane. While acetonitrile is a polar solvent, N-hexane is nonpolar. So if the environment plays a role and we are observing a spectral shift due to solvation, then we would expect a huge change of what we observe in the acetonitrile compared to the N-hexane. Here is what we observe. You can clearly see that the shift of the stimulated emission is identical for the two solvents. From this, we can then conclude that this motion that we observe here in this spectral shift is actually due to a synchronous motion of the molecules. With the help of theory, we can actually find out that it is the synchronous motion of the molecule from this configuration to this more stable configuration of the excited state of the molecule. And then this configurational change is followed by another step that then makes the molecule reach the final configuration of this first molecular motor movement. This alone was already very exciting for us. But on top of that, we also found out a really surprising truth about these molecular motors. We looked at all the data that we extracted, and we could model the dynamics of this molecule perfectly with a simple mechanical spring model that works under load and is overdamped. And that was so surprising to us, that you can model molecular motion that is determined by quantum physics at the nanoscale by very, very simple mechanical models. Thanks for watching.